The code in the Linux kernel changes all the time. 11,000 lines are added, 5,800 lines are removed, and 2,000 lines are modified daily. Linux is an open source operating system that has been worked on for 25 years, and one reason that the project is able to move so fast is its governance and release structure. Greg Kroah-Hartman is a fellow at the Linux Foundation, where he takes part in many of the developments in the kernel. This episode was a dive into how open source software gets built at scale and what is in store for the future. The Kubernetes project has drawn comparable attention to the size of Linux, and the Kubernetes project is learning how to manage open source from the Linux community. If you're looking for old episodes of Software Engineering Daily, but you don't know where to find the ones that are interesting to you, you can check out our new topic feeds, which are in iTunes or wherever you find your podcasts. We've sorted all 500 of our old episodes into categories like business or blockchain or cloud engineering, JavaScript, machine learning. We also have a greatest hits feed if you're just looking for the best episodes across all categories. Whatever the specific area of software that you're curious about, we have a feed for you. So you can check the show notes for more details. And I hope you liked today's episode. Spring is a season of growth and change. Have you been thinking you'd be happier at a new job? If you're dreaming about a new job and have been waiting for the right time to make a move, go to hired.com/sedaily today. Hired makes finding work enjoyable. Hired uses an algorithmic job matching tool in combination with a talent advocate who will walk you through the process of finding a better job. Maybe you want more flexible hours, or more money, or remote work. Maybe you want to work at Zillow, or Squarespace, or Postmates, or some of the other top technology companies that are desperately looking for engineers on Hired. You and your skills are in high demand. You listen to a software engineering podcast in your spare time, so you're clearly passionate about technology. Check out hired.com/sedaily to get a special offer for Software Engineering Daily listeners. A $600 signing bonus from Hired when you find that great job that gives you the respect and the salary that you deserve as a talented engineer. I love Hired because it puts you in charge. Go to hired.com/sedaily, and thanks to Hired for being a continued long-running sponsor of Software Engineering Daily. Greg Kroah-Hartman is a fellow at the Linux Foundation. Greg, welcome to Software Engineering Daily.
Great, thanks for having me.
Describe your responsibilities in overseeing the Linux kernel development.
Overseeing. I have a role within the Linux kernel community. I don't necessarily oversee stuff. I am a kernel developer. I'm a maintainer of different portions of the kernel. And I also am responsible for releasing the stable Linux kernels. Linus does a development kernel about once a week, and I do a stable kernel about a couple times a week.
And we'll get into what some of those terms like
Sure.
stable kernel mean. Continuing with this overview of the Linux kernel, Linux is 25 years old. How has the project changed over that period of time?
Oh, wow. It's changed a lot. Basically, the biggest thing to look at how we change is how we manage the project. I mean, the project used to be managed, we'd email Linus some patches, and we'd hope in a week that they would show up in his tree because he'd release a tarball. We'd readjust and resend them in again. Now we use Git. We actually created Git based on the need for the Linux kernel. That came from how our development model worked. And we created this big, giant ecosystem of developers. We have, 4,000 developers last year that contributed to the kernel. Before, we used to not have that many at all. So it's grown immensely. So we've been able to scale and grow, and we pretty much took over the world.
How has your role in the Linux project changed? How has it evolved over time in tandem with the evolution of the scale and the tools that you've had available in the Linux project?
Yeah, so I started off as a Linux developer. Then I contributed a few patches to the USB subsystem. And then I wrote a driver for some hardware that I had. And started maintaining that driver, and then over time started maintaining the subsystem for those drivers, which was the USB serial drivers, and then started maintaining USB drivers. I got a job doing this Linux kernel work, and over time just started sucking up more and more driver work and contributed more and more things, and then eventually we came up with the model of doing stable kernel releases. Mm-hmm. And I can talk more about that. And I was one of the persons to start that, and I've continued doing that since then, over a decade now.
Yes, I do want to get into that eventually. So the thing that's interesting about Linux, well, one of the many interesting things is that it's used in laptops, smartphones, a lot of other devices, and I'm not sure if that was on the roadmap in the initial creation of Linux, but does the proliferation of these new device types affect the contents of the kernel?
Totally. And we have no roadmap. I want to make that clear. Everybody asks, what's going to happen next? We have no idea. We want to make whatever is going to happen today work well today, and we'll worry about tomorrow then. So yes, we've made the kernel work for all devices, and it's a big deal. Everybody thinks their little problem area is special and unique, and I like pointing out the fact that, like power management, the embedded devices people came to us many years ago and said, we need better power management. We need to be able to control power better. We need to be able to manage it better. And here's this neat patch, and here's this change to the kernel, and it's over in our little corner. And people pushed back and said, no, you need to make it generic for everything. All devices need it. Maybe laptops might need it and some not. And it turns out the biggest users of that are the mainframes because they use the most power. And there's like real money in the power that those use. So you can shut the different parts of that down. And we got it in the kernel, and it touches everything, but it works for everybody. So one change works for everybody. And that's what's made us evolve and work really, really well over time, because we've forced developers to make it work for everybody.
That's true for something like power consumption, but what about something for self-driving? For example, being really good at image recognition. Is there something in the kernel that you might want to adjust to improve the image recognition? And that's something you wouldn't necessarily want in server aside Linux or maybe in Android smartphones, but you want it in some domain-specific versions of Linux.
No, not really. So, the kernel is written such that it handles all hardware out there in the world, right? That's how we've really succeeded, is because we work for all devices, but they're configured for all different types of devices. Your server doesn't configure the Android code, right? Or your random audio device. For that kernel, you can configure the kernel in many, many different ways. So audio or image recognition, you only need one or two special drivers, or the drivers for the hardware that you're using, and away you go. The kernel is actually, for image recognition stuff, it's just a really dumb conduit. It just gets out of the way and lets your GPU and everything else run fast.
Okay. You mentioned that there's no roadmap, and I find that interesting. There are some software projects that have really succeeded with no roadmap, like the Linux kernel. But if you were talking about a company, if a company were to say, we have no deterministic roadmap for the future, we're just latching on to whatever is kind of the local minima or the local maxima of demand, the shareholders of that company might go crazy. Is there something about an open source project, or maybe Linux specifically, where this modus operandi of not having a roadmap works?
Well, yeah, because Linux is contributed to by many, many people. 4,000 individual people, over 400 different companies last year, and everybody contributes in a very selfish manner. Everybody wants to get their problem solved. So, as a maintainer of a subsystem of the kernel, we see it when people propose their solutions to these problems, be it new hardware, be it different domains that Linux needs to run in, or larger memory, or whatever. So companies have their own roadmaps to get their own hardware and their own solutions accomplished, and then they post the code to us for our review, for our acceptance and critique based on that. So we kind of just go with the flow. We handle the new hardware that shows up. We handle the new code that shows up, and we do that. We can't really plan for the future that way. Now, that being said, we are told of we know what new hardware is coming. Companies sit us down and talk about, hey, there's this neat stuff coming, like NVMe, that memory bus stuff we knew about years ago. And we said, that's great. Show us the hardware, or show us the drivers, and it goes from there. So open source is neat when you have lots and lots of different companies contributing because they all contribute in a way that's specific for them, but it works out for everybody.
I see. So you can trust in the long-term visions of those companies and find the intersection of highest cardinality among those things, and those will allow for something that resembles maybe a long-term vision that you don't even realize, or a long-term vision that manifests in short-term decisions within the Linux kernel.
Sure. And that's how I talk to a lot of companies. I go around, part of my job at the Linux Foundation is to going and talking to companies, telling them how they can contribute to the kernel, how can they participate. And the main reason companies want to participate is you as a company are using Linux in a very domain-specific way, be it like for a windmill, like all the big windmills use Linux, or a mega yacht, super mega yachts use Linux for their guidance control systems. So you've made changes to Linux and you want to get those changes back and accepted because you have to trust yourself that you're driving Linux forward for you. If you don't contribute back, you have to trust that all the other companies that are contributing are driving it in a way that's good for you. Now, ideally, you do trust. You trust Intel and ARM and AMD and Qualcomm and all these SoC chip manufacturers to make their hardware work well. But what about the other core things like the different scheduling ideas and people like that? If you're not contributing to that, then you're going to have to take their word for it and take their code for it, which is fine. And a lot of companies do trust that. But I try and say, wouldn't it be nice for you to control your own destiny and participate?
You are an advocate of a stable API between kernel and user space. I think I cribbed this directly from Wikipedia. There's a lot of people listening, and I would actually put myself in this bucket, who really don't know a lot about Linux. Like, we've just worked with Linux as people who are building web apps, and this is like the thing that we're sometimes deploying our web app on. And beyond that, we know like, okay, you can use sed and awk and like some other stuff on the command line, but we don't really know much about what goes on underneath. So, just so we can have a little bit of a common language, there is this kernel and this user space. What are the responsibilities of these two areas of Linux?
So the kernel is there to do it. Basically, all a kernel does is manage resources, and it makes your hardware look like something in a very consistent way. So it makes all mice look like all other mices, all other mice, or whatever. So a kernel makes the hardware look in a common way, so you can write your application, and it'll run on any Linux machine that's out there. Right? You don't really care what the underlying hardware is. You don't care what the disk is. You don't care how much memory you have or what kind of keyboard you have. They all just work. So that's one job of a kernel, is to manage like all the hardware and to manage the resources, to manage your files, to manage the file system that your backend, your storage is on, be it a local disk, be it a remote disk, be it a cluster, be it whatever else. The kernel is there to abstract and give you a common API in which to work with these resources, be it files or memory or a mouse. So yes, we need a very stable API there. So we need an API that you write a program and it's going to work for forever. So that's our main goal. Is I have programs that were written in the 90s, that were compiled in the 90s. They still work just fine on Linux. That's our goal. We want to keep that API stable. And in fact, that's the only time when Linus gets mad and curses at people, is when that API is broken on purpose. If we accidentally break it, great, we'll fix it. We accidentally break things all the time. But if we break it on purpose, then we get mad. And then the cursing happens. But that's it. That's the only time.
And when Wikipedia refers to you as an advocate of a stable API between kernel and user space, this sounds like something that is non-controversial. Is it the fact that you're an advocate in response to perhaps when somebody submits a push that is not, it's not like they're, or a pull request that is not necessarily, it's not like they intended to like have a fuzzy API or an inconsistent API between kernel and user space, but because they did a rush job or something, you have to reject the pull request and say, this is just not cleanly partitioned, or what does it mean that you're an advocate of this thing that it sounds like everybody would take for granted?
I don't know. I haven't read my Wikipedia page in a long time. But it is in some areas. We make mistakes. It's really hard writing. In the early days, we all were chasing Unix and we all know what we needed to do. That day has been passed like about 10 years ago, and we're in the forefront now. Creating new user space APIs to solve problems is hard, and we get it wrong usually. Getting it wrong means we still got to keep around the old one and make it, modify it in a way that's not going to break somebody. Michael Karras, who maintains our man pages, which is the documentation of this user to kernel API, has a really, really good talk out there on how to make a good API and how to make a good API in a way that's going to be future proof, and that if we mess something up, on how we can recover and fix it and go forward. And he's given that talk at a number of Linux conferences over the years. He's also written a really, really good book of the Linux Programmers API. I don't remember what the name of the book is, but it documents this whole API between user and kernel space. But So I wrote a document a long time ago in the kernel talking about the internal API that the kernel has. And a lot of people advocate that the internal API between like the kernel and drivers should be stable so that they can write a driver once and it'll work for forever. Other operating systems, they claim, have stable APIs for drivers. That way you can have your driver outside the main tree and it'll still work. I'm a strong advocate that that is not the way to go. And Linux, we refactor our internal API very, very hard. We do it with total abandon. If we see something that needs to be changed, we'll fix it up everywhere and keep on moving. So our internal API changes all the time. So the main goal of all drivers in the kernel and all code needs to be merged into the main kernel. Because if I change an API in the kernel, I'll fix it everywhere. I'll fix it in your driver, but I also see commonality. So if we have 3 drivers for something that almost looks like the same hardware, hey, we can merge all these 3 together, save code, save space, and move on, and we can reiterate and refactor. And because of that, Linux drivers are about 1/3 the size of other operating system drivers, because we can do that. And 1/3 the size is great, less code, that can be less memory and less bugs. So I'm a strong advocate for a stable API outside the kernel, but a very broken one inside the kernel.
Angular, React, Vue, Knockout. The forecast calls for a flurry of frameworks, making it hard to decide which to use. Or maybe you already have a preferred JavaScript framework, but you want to try out a new one. Wijmo and Grape City bring you the How to Choose the Best JavaScript Framework for Your Team ebook. In this free ebook, you'll learn about JavaScript frameworks, you'll learn about software design patterns, and you'll learn about the advantage of using frameworks with UI libraries like Wijmo. You'll also learn about the basic history and the purposes of JavaScript's top frameworks. You'll also learn how to integrate a Wijmo UI control in pure JavaScript and in some of the top JavaScript frameworks that we've already talked about, like Angular, React, Vue, and Knockout. Wijmo's spec method allows you to determine which framework is best suited to your project based on your priorities. So whatever those priorities and your selections are, you can learn how to migrate to a new framework in this ebook. Best of all, this ebook is free. You can download your copy today to help choose a framework for your work at softwareengineeringdaily.com/grapecity. Thanks to Grape City for being a new sponsor of Software Engineering Daily. And you can check out that ebook at softwareengineeringdaily.com/grapecity. I just put a note to send an email to Michael Karras because that sounds like quite an interesting topic, his discussions around APIs. You know, we've had a lot of shows about microservices and distributed systems and how companies scale that because it's a hot topic. You're talking about keeping a contract between 2 maybe divergent systems clean, but aggressively updating an internal API. You know, there's a lot of discussion around these distributed systems, whether you should version APIs and when and if you should version it. Do you ever do versioning where you maintain an old API and you have certain things that are making requests to the old version of the API and certain things that are making new requests?
Oh, totally. We have like many syscalls that have a 2 at the end of them because we've learned over the ages, and even POSIX. I think POSIX has a few of those as well. That they define that API as, oh, we need to make a new one, and here's the second one, or here's the open with additional parameters and it open at function instead of regular open. Yes, we do that all the time. We add another one and move on. And then internally, you can usually rewrite the old call as a subset of the new call, and it works just fine. So yes, we have to maintain that. And so we provide that guarantee because we want people to be able to update their kernel without having anything break. And we don't want you ever to have to rewrite your code because of something we did, because that's just mean, right? I don't want you to have to do that. And that's something that a lot of software projects fail at. And that's hard. It's hard to do. I agree. We're lucky in that our API is very tiny, relatively speaking. So we don't have to have as big of a problem there. But it's very important if you want users that are going to continue to use your product. We also guarantee that we're not going to break your system. So we want no regressions. We will always fix a regression over a new feature. We'll rip out a new feature that broke something and put it back the way it was at a drop of a hat, because we do not ever want you to be able to, if you upgrade your kernel, for something to break. We never want that to happen. And people have tested that. I think Facebook tested that a long time ago for the stable kernel releases. Over like 90 releases that I made with stable kernels, we never broke anything. We made that guarantee about over a decade ago, and we've been doing really, really well there.
I want to discuss the governance and the contribution process of Linux. You've defined this term stable kernel a couple times, or you've mentioned it. Could you define it?
Sure. But shall I talk about how our development model works, because it fits into that at the same time?
That would be great. That would be great.
Okay. So you start off with a developer, or somebody wants to make a change, be it you see a spelling fix or you want to add a new driver. Per se, you got a new type of a mouse. You make a change to the kernel and then you email it in. And those developers, we have about 4,000 developers last year contributed to the kernel. So you email your patch on a mailing list, not using Git. You can use Git internally, but we don't take pull requests. So we just want email. And we use email because it scales. It scales much, much better. I mean, we're averaging, our acceptance rate for patches is about 8 patches an hour. And we only really accept about 1/3 of the patches that are sent to us. So 2/3 larger number of the patches that's sent to us. So email. So you send email to the patch for your change to the owner of that driver or that subsystem. And all drivers and subsystems in the kernel have an owner. Maybe it's somebody who wrote it first, or so say USB, I maintain the USB subsystem, but the USB serial subsystem, which is a subset underneath me, is maintained by somebody else. So you send it off to there. There's a public mailing list for every different part of the kernel. We all have small mailing lists. There's a huge giant mailing list, Linux kernel mailing list, that we all kind of filter. Nobody reads it. That's a little dirty secret. It gets about 400 emails a day. But so those people send a patch off through email. It gets reviewed. It gets accepted or rejected. You revise it, resend it. And then eventually the maintainer of that subsystem accepts it. And then the maintainers of subsystems, we have about 150, maybe 200 of those. No, sorry, 700 maintainers. And then they have a kernel tree, and then they push up to a larger subsystem tree, and then we have about 150 of these subsystem trees. These are all public on git.kernel.org, and all the patches go into there, and then they get merged once a day all together by somebody in Australia. Stephen Rothwell merges them all together and produces what we call Linux Next. And that is where we see all the problems that are going to happen. This is our development tree. And we see where the merges happen, see the problem. So, for example, if I make a change in a network driver in my USB subsystem, the network maintainer was making an API change. We'll see that error there. We'll see that problem. So that's how we do it as far as what we do every day. These trees get built. They get booted on virtual machines and see how, if anything, shakes out. During the merge window, and I can talk more about it in a minute, Linus has a merge window. When he does a release, for 2 weeks, all the maintainers of these subsystems send all his patches, all the patches that we have ready for him, to him. And then Linus does a new release. We call it Release Candidate 1, RC1. And then for every week after that, Linus does a new release candidate 2, 3, 4, 5, 6. Once a week, he's doing them on Sundays. Every release he does from after Release Candidate 1 is bug fixes only, or regressions. We'll revert something, we'll rip something out. Bug fixes only. New release candidate for up to about release candidate 7 or 8. looks good and solid and stable, Linus will do a new release, and then the whole thing starts over again. The maintainers throw all the new stuff at them, and away we go. So we do a new kernel release about once every 2.5 to 3 months. And we've been doing that for about 10 years. And we do timed releases. So we do a timed release this way. So timed releases are great in that as a maintainer, I don't have to feel pressure to accept a patch from somebody if it's not in a good enough state. Because if I can't accept it this release, I know 3 months from now he can get it in. It's good because if I had a 2-year window or even a 1-year release window, I'd feel a lot of pressure because that's a long time to wait between releases. So that's how we do our development releases. Linus does a new release, and away we go. Now, about a decade ago, we realized with these releases from Linus, during those 2.5 months, bugs happen. We got something wrong, security bugs happened, something else happened. So what do? So I'm the maintainer of these stable kernels, so I fork off Linus's tree, and then I take patches that are in there for stable kernels. And I do a stable kernel release about once a week. I have some cool drawings about how this all works I can show you in the presentation as well. And the rules for the stable kernel are the patch has to be in Linus's tree. And we make that rule that it has to be in Linus's tree so we never diverge. We never want a patch to go into a stable kernel that isn't in Linus's tree, because when you update to the next version of Linus's tree, you also want your fix to be in there as well. And I do stable releases, and then after Linus does a new release, I will usually drop that old stable kernel and then go on to a new one. So that's how we have stable kernels. People like these stable kernels, and they build products on them. So if you look at your distros are all based on these stable kernels. Phones and Android devices are being built off of long-term kernels. And long-term kernels are something that we've picked up over the years. Is I'll maintain one of these stable kernels. I'll pick one of them a year, and I'll maintain it for 2 years. So we backport all the fixes to the older kernels, and then that way older devices that are a year or 2 years old, will constantly have stable or bug fixes and security updates as the time goes on. And that's a really good thing.
Could you zoom in on the relationship between release candidates and stable kernel? Maybe define release candidate for the audience.
So release candidate is Linus's tree. We threw a whole bunch of stuff at him for 2 weeks, about 10,000 patches. And so he does, it looks good to me. Let's get a release candidate out there. Release candidates are what the next major kernel release is going to be. And then it's the accumulation of about 2 to 3 months worth of work for people. 10,000 changes is about usually per kernel release. That's a release candidate. So it has new features, new drivers, new subsystems, lots of new stuff. Stable kernels are bug fixes only for the last major release. So the rules for a stable kernel is it has to be a fix that's obviously correct, usually less than 100 lines long, and it fixes something that people report. Or it can add a new device ID. So say you got a new type of mouse that just adds a new item to a table somewhere, we'll take those as well. But stable kernels just get bug fixes only, and that's it. No new features, no new additions like that.
Throughout this release process, what tests do you have in place? Do you have automated tests, manual tests? What's going on in the submission process and release and testing?
Tests. Testing is interesting. A lot of people are finally waking up to that one. Many, many years ago, we used to have a lot of tests going. A lot of companies were running tests, and they came up with the Linux test project, which was written to cover like all syscalls. Some driver subsystems had some tests. There were some stress tests for networking and file I/O. And then over the time, everybody thought everybody else was doing the testing, so they stopped testing. So about 4 or 5 years ago, we realized nobody was testing, and that wasn't good. So Intel stepped up, and they created an engineer there created something that we call the zero-day test bot. And I think it's just this giant server farm of CPUs that are idle. And what he does is he goes through all our developer trees, all the Git trees, and he boots them all, builds them all, boots them all, and starts running tests on them all. I mean, booting a kernel is a non-trivial task. So if a kernel boots, you're usually pretty good. But we boot and build tons of different configurations, architectures, and then he runs tests. I think there's a whole bunch of performance tests on there to run for longer periods of time. But this bot that's out there is amazingly fast. I can push a Git tree out, and then an hour later, I'll get something back saying, hey, out of these 100 patches you just pushed, patch number 65 had this build warning over here, and patch number 72 broke the build in this way. Go fix it. It's amazingly good. So those are build tests. We also have a lot of static analysis tests. And static analysis is you run through the code just to check the code. You don't actually run it. So these look like a C compiler. We have something called Sparse that Linus created, which is a C front end. There's something called Kernel from Julia Lual here in Paris, which is one reason I'm here in Paris. You can write rules for this tool that analyzes the source code for common patterns that we know are wrong. I mean, she's written tests for the kernel that have fixed more security bugs than anybody else because of this. And once we write a test, we add it to the test suite, and then that prevents any new code that comes in with that same kind of pattern from ever being able to be introduced again because we catch it. And we have hundreds of those tests. We also have tests in the test subdirectory of the kernel. We have a maintainer of these tests now, and they test specific functionality. So like if you add a new syscall to the kernel, we can exercise it, make sure it works properly. So between all those tests, all the developers' trees are tested, Linus's tree is tested, and Linux Next, where we merge all these together, are all tested every day. It's really good. So we test a lot of different things.
Do you feel comfortable with the automated test coverage, or do you feel like there's also a necessity to do a certain degree of dog fooding and perhaps manual testing?
Oh, we have to do manual testing. So I'll give an example. It turns out that we have a test suite called Linux Test Project, LTP. We finally ran it on some ARM64 machines, an old kernel, and found a bug that got introduced over a year and a half ago. It turned out everybody was running it on emulators and never on real hardware. And it was a timer bug. It was a very nuanced, high-resolution timer bug, but that would only show up on real hardware. So yes, you have to debug, or you have to dog food on real hardware, because there's also flaky hardware. You can only do so much with emulation. You can do a lot with emulation. The graphics guys have some amazing emulation that they do for graphics tests. Do you really need real hardware? And so there are people out there. So there's a group called Kernel CI from Bay Libra's the company, and Lenaro also contributes, and they test, and they have a couple hundred different ARM machines that boot and build and boot all the kernels all the time. My stable kernels, Linus's kernels, and a whole bunch of other things. And the ARM developers have a whole bunch of test systems that they build and boot on. So you do need real hardware as well. And I mean, I test all my kernels and stuff on my laptop. Again, booting a machine, a laptop, is a non-trivial task.
The Women in Tech Show is a podcast featuring technical interviews with prominent women in technology. The most recent episode features Karen Walker, former VP of Operations at Compaq. She talks about working on the largest supplier of PCs in the 90s. With the Compaq Portable, they took on IBM and became one of the fastest growing companies in American history. Other great recent episodes have covered subjects like robotics, distributed systems, and ethical questions of artificial intelligence. Check out The Women in Tech Show on iTunes or wherever you get your podcasts. At companies, the widely accepted strategy of breaking up the company into teams of different projects, I mean, it's not universally accepted, but there's a lot of companies that do this 2-pizza team thing where there's like, maybe 10 people max or 12 people max on a team. It seems like that might be less important on a completely decentralized project. And could you just talk some about how teams or specific modules in the Linux kernel are managed by different people? I'm interested in the dynamics of the different sub-teams involved in the Linux kernel.
Sure. The Linux kernel you can think of it as a pyramid, right? So there's 10 USB developers, and they send patches to me. I send patches on up above that, and you go on up above that. Look at the networking system. There's wireless developers that send it to the wireless subsystem maintainer. He sends it off to the main maintainer of networking, and then he sends it off on up to Linus. So it's a bit of a pyramid there. But we're all people, right? And we have human interactions, and we've learned over the years that we need to get together and talk and meet each other, because all we ever used to do is see each other through email. So about 12 years ago, Ted So finally realized that and created the Kernel Summit, where we all got together and meet each other for the first time. So it's a hierarchy of people accepting changes from other people, passing them on up the stack. I take patches from people I know over the years, and I trust, and I don't necessarily trust that they got it right, but I trust that they'll be around to fix it if they got it wrong. And that's the important thing. You have to trust that somebody's going to be there to fix the problem. Because when I accept your changes from somebody who submits it to me, I'm now responsible for it because my name is on it. I signed off on it. It goes on up the chain that way. So hopefully you're going to stick around because I have enough code of my own to maintain. So it's a personal dynamic. It's meeting people and realizing that they're going to stick around and do that, which is hard for some subsystems. Some subsystems of the kernel is very hard to get changes into if people don't trust you. They don't know who you are. Networking is a huge example. The scheduler is a huge example. And networking is it was proven itself. Many years ago, a new feature finally landed in the networking subsystem, a big, hairy, nasty feature. And the day after it hit the tree, and was finally merged, the email address behind that disappeared. And it took the developers 6 months to unwind the mess and fix it all up probably. So it is very, very hard to get a networking core change in for somebody who's brand new. It's not that we don't necessarily trust that you got it right, but if you got it wrong, are you going to stick around and fix it? So you have to accrue trust, and you have to start off small, start off by reviewing other people's patches, start off by integrating yourself, go to the conferences, we all travel, we all meet each other, say, hey, look, I'm a real person behind this, I'm looking to do this, talk to us, and go from there. And yes, it is managing. I trust some people above me, Linus trusts some people. So again, 10 people is about how much a normal team you can work with. That being said, there's some of us maintainers that do accept patches from a huge number of different people. The networking maintainer ends up accepting patches from large numbers. I end up accepting patches from large numbers due to some of the subsystems I maintain, where there are a lot of just drive by, fix up a tiny thing and go away, which is fine. Those changes are great. We love those changes because we never know where a new developer is going to start from, right? A nice, easy, simple spelling fix is a great place to start, and they can like that and keep them going on to something else.
I believe there are some interesting lessons in company management that can be derived from the Linux kernel management. Again, not lots of direct conclusions, but certain perhaps inspirational things. Do you have any ideas around what is the, like if you talk about this pyramid where there's somebody at the top and then there's different layers of people who are, changes are bubbling up, and these different people at each layer of the pyramid are aggregating those changes and checking them against other people. Do you have any beliefs about the branching factor of that pyramid, or how deep you can go before it becomes just too many layers of management between the top and the bottom?
Yeah, it's not as deep as it sounds. So I actually graphed this one year. I posted it was a giant, 2-meter tall by 10-meter, 20-meter long graph. It was a huge mess. So we talk about it as a nice, neat pyramid, but the routing of way patches go through the kernel it's crazy. It's a huge, giant network graph, which is good because sometimes as being a maintainer of a subsystem, it's not the ability for me to say no to something. So like the networking maintainer can make changes to the USB subsystem if he thinks that's what needs to be done. So if he's nice, he'll ask me, do you think these are okay? And I'll say yes or no, and then we'll go from there. But it isn't an absolute control. So we don't have nobody has absolute control over their subsystem, and that's a good thing because people go on vacation, people get sick, people pass away. We've had maintainers that die. Life happens. So you can be routed around, which is good for the stability of the project. That necessarily isn't the same thing as in a company. You can't usually have that. We don't really have managers per se. We have people that are maintainers of subsystems, and we impart taste on how we know things work based on our experience. And that's also another thing Linux has that no other operating system has. We have people that have been working on these things for much, much longer than anybody else. At a traditional company, if you stay 5 years in the same group, something's wrong, right? You have to move on and learn other parts of the company. I mean, I've been doing USB since the 1990s. The networking maintainer's been doing networking since the early 90s. If you look at the depth of knowledge of what we have in Linux kernel, it's crazy how long people have been working on these domains and knowing it. Because we even move to different companies and we take the subsystem and we take the maintainership with us because it's done as individuals, not as a company. And that's something that companies need to learn when they join the Linux kernel. one company I worked at, somebody was assigned to one subsystem, and he ended up becoming the maintainer of it. This is great. And then he was supposed to go, his company wanted him to go off and do something else. We're like, no, wait, he's still the maintainer of the subsystem. He still has to do this. And then he did that, and they had to carve out the time. And then he changed companies later on. And then he took that maintainership with him. And he's still doing that same type of stuff because he enjoys it. But that's the knowledge is there, and the depth of knowledge is there. So we respect each other, but we can modify each other's code. We can be routed around, and things work that way. So it isn't the traditional development model. That being said, I think Harvard Business Review has written a number of papers. I used to joke that a lot of people should be able to get master's degrees based on look at our development model, and it has. Now, I think there's been a number of different theses or papers and have been written on how our development model works over the years, which is great to see.
I read an article about your work with the Kubernetes team. How is the Kubernetes project similar to Linux?
They're similar in that they're really successful right now, but they're also, they hit the wall on number of developers wanting to contribute really, really fast. GitHub is a great place to work for maybe if you have 10 people on your project, but Kubernetes has so many people on your project. GitHub does not scale well. Docker hit this wall a long time ago when I worked with the Docker community to try and help them figure out to change their development model. Kubernetes hit it really, really, really fast. So they had a very, very short term to get their ecosystem changed based on the kernel's evolved this way over over 25 years. They're hit the ground running. So I feel sorry for them in that sense. That being said, they're doing a really, really good job in trying to handle this stuff. They still have growing pains. I still talk to them a lot. I help out in advising them when they ask me questions. But it's tough. It's tough to scale a project really, really fast. We've had experience doing this, and it's slowly evolved over time. They're having to do it very, very quickly.
You've said this a couple times about how a repository management tool like GitHub might not scale if you have a project that's big enough. What are the specific pain points of anything that is not email, basically?
Oh, I actually gave a good talk at the Kernel Recipes Conference last year about how all these tools suck for high-speed development besides email.
I assume you're including Gitter and Slack and like all these different things.
Slack, maybe. Yeah, Slack is IRC. We all use IRC. There's kernel IRC channels. There's the kernel newbies channel, which is great if you're learning kernel development. There's a kernel newbies IRC channel. There's like 400 people in it. Nobody's talking. Just ask your question and it'll be answered. But no, we use that. Slack is fine. I'm talking about things like Garrett. Garrett is horrible for submitting patches and review. I know people use it. In dealing with the Android developers, I'm getting more and more used to it, but it's still pretty bad. It doesn't scale very well. For GitHub, it's hard to do patch review, right? Patch reviews in silos of this individual patch. It's hard to see if you maintain an area of the kernel. You can't just watch everything go by and contribute where you want to in an easy way. You have to click around, drill down, and do it. That being said, GitHub has worked a lot. They've worked a lot to try and make it easier. You can now use email along with reviews on GitHub, but it's hard. It's a hard thing to do. Not everybody can just use emails because there are managers out there who want to see what the outstanding issues are and where things are, what state certain patches are in, and so on. There are some really good tools that people have written. There's something called Patchwork that works on top of a mailing list, and a number of kernel subsystems use this, like networking. So when you email your patch in, you can then go look on the web page and see what the state of the patch is. You can see has it been reviewed, has it been accepted, yes or no, where it is in the response. Do I need to do something else with it? So there are tools on top of email that work really well also. People are used to thinking, of email in some client like Gmail, which is a horrible, horrible client as far as dealing with large numbers of email. You need a better email client. There's a lot of better ones out there. We've been using these for a long, long time. For example, I get about 1,000 emails a day for non-mailing list stuff that I need to do something with. I can handle that trivially in my email client. Gmail would just choke hard. I could never do that.
Yeah. You talked earlier about how other changes to the world impact the Linux kernel and cause changes to be made in the Linux kernel. Does the rise of Kubernetes come back to impact the Linux kernel?
Not that I know of. I mean, if you look at Kubernetes, is just like basically an application on top of containers that manage containers across the network. I mean, it's a great, useful tool. It's very helpful. I don't pay attention too much to the networking subsystem, but I know the networking namespaces, and there's been other namespace kernel patches over the years that have helped these people out, have helped containers out, has helped Docker out, and by virtue of that has helped Kubernetes out. So that being said, that we do run containers very well, and those were thanks to low-level kernel changes that were made years ago. I'm sure that bug fixes come in every once in a while as well.
I'm someone who has seen containers get a lot of headlines and be used as this distributed systems management unit that gives me some better usage of my infrastructure. But as I understand containers, they've been around for a long time. It's nothing new. What's new perhaps is the usability or the applicability to managing a distributed system. Can you talk about how containers have played a role on within Linux, do I have containers running on my desktop Ubuntu? Are they doing something just in a single system?
No, they're not. So in a single system, they're not. Some people are working on to change that because there is some nice partitioning and a tiny bit of a security barrier you can put between applications that way. I think Android does something like containers. I'm not quite sure how their user space works for applications, but their applications are very siloed in a container-like way. I think when you run Android on top of Chrome OS, those are using containers as well. A regular Ubuntu desktop, OpenSUSE or whatever, no, you're not using containers. The weird thing about containers is a lot of the work that's done with those to handle this container can't go over so many percentage of my CPU happened in the kernel years and years ago, something called C groups, which was container groups. And that work came from IBM and some other places where large systems were trying to be divided up into smaller ones, and they wanted to be able to partition stuff away. The S390 big giant mainframes that run Linux drove a lot of that work. I always joke, if you want to see where Linux is going, look at what the S390 guys are doing, because they seem to solve our problems about 5 years in advance of everybody else. They did the container work first, they did hot plug first, they did 10,000, 20,000 SCSI devices first over the years. These things came out of the mainframe world, and now they work for everybody, which is great.
Piecing together a few things that you've just said, you can tell me if this is incorrect, but are you saying that the idea of a C group, so when I hear people talk about containers, okay, it's a container is a namespace in a C group, and then what you said is C groups are this way of, it's like an alloc. It's like a allocation of memory or resources that you're giving to an application or something that's running. And you said that the idea of a container, like a Docker container, is really more about the networking among different systems. And that's why, maybe you don't necessarily need this abstraction of a container on a single machine, because the networking architecture going between different machines is really the big deal with different containers. Am I getting that correct?
Well, kind of. So what Docker did really well, and everybody says Docker is just a really simple thing, but what they did really well was they pulled together the fact that you can have different network namespaces. So on a same machine, you can create a network namespace that this network is only talking to these processes, and it's going to look separate from the other processes. They can't see the same networking connection, as well as a file system namespace. So you can mount a file system in a specific location on the disk or in the large file system, and you can't see outside of it. So you can't break outside of that area. Combined with things like process isolation and the C group stuff, we're saying this process, I'm only going to be able to allow it to never go over 50% of my CPU usage right now. I'm never going to allow it more than 2 GB of RAM. So it can't take anything away from anything else. So Docker bundled all that up together in a cool tool that said, here's your file system, here's your network, you're creating these namespaces, and here's the resources you're going to provide for this, and away you go. And it runs one process inside that, quote, container that's network isolated, it's file system isolated, and it's memory and process and other resources isolated. So Docker, and then by virtue of that, Rocket and these other container engines bundle that up in a nice way. And then Kubernetes on top of that just makes it so you can take your container, which is just one process, and move it around the network in a resource way. because you want to have like 20 mail servers running at a time, things like that. So the kernel provides these little tiny building blocks, a Docker and Rocket, then combined into another building block that you run your process inside of, that Kubernetes then manages on top of that, and so on and so on.
One of the themes of computer science, and it's been a theme in Software Engineering Daily, is the idea of schedulers and scheduling. And this is a problem area that is just evident at all layers of the stack. What have you learned about schedulers from the Linux kernel? And has there been any application from that knowledge base that you've gotten from working on schedulers in the Linux kernel to in your conversations about Kubernetes?
So when I think of a scheduler, I think of a process scheduler. So on the kernel, Linux is a multi-process machine. So the goal of the scheduler on the Linux kernel is to run as many processes that are waiting to be run as possible. If a process is waiting for some I/O to happen or some networking, basic I/O file or disk or network to happen, I don't want it to run because I'll just sit and busy wait. So a scheduler's job is to run everything as good as possible. The Linux kernel has had a number of different schedulers over the years. And if you look in your device, your phone, they usually wrote a different scheduler for that because phones, devices want to take power management into the scheduling equation. They want to be able to make sure that the power usage of a certain process, if this process is going to take a lot of power, we need to run it a certain way. So they modify the scheduler based on that. And then there's changes upstream that are going in to slowly make that happen. You can have processes that have different priorities, be it like a real-time priority where you have to be accessed every X number of time, or I want to run as fast as possible, then get me out of the way, or just run me whenever you can and there's a free time in the system. So that's what I think of schedulers. There's also networking schedulers to handle networking queues and disk schedulers to handle your disk queue, because the disk is really just a whole bunch of packets going down that are being read and written to a device. So you need to be able to schedule those. You can sometimes coalesce them into a larger request or split it up into smaller ones and go on from there. So the kernel has different networking schedulers. They have different block schedulers. They might have networking. I don't know networking that well. So when Kubernetes talks about scheduling, that's a totally different type of thing. But in a way, it is managing resources of processes, right? You want to be able to make sure that you have 20 mail servers running somewhere. So if one disappears, or do I schedule the next one to run, right? So it's the same idea of resource management, but it's just in running processes in different places.
You've mentioned this dynamic that corporations have with Linux, where the corporations have their long-term goals, and those long-term goals get aggregated and they kind of manifest in short-term decisions in the Linux kernel and asymptotes towards a long-term vision for those different companies. Do you have a sense for how that compares to the corporate interaction with Kubernetes? Because certainly look at Kubernetes and there is a frenzy of opportunity around, like, companies that are being built around Kubernetes, on top of Kubernetes, making enterprise distributions of Kubernetes. What's the interaction that you see between corporations and Kubernetes? Is it the same as what it was with Linux?
Well, I hope it's the same because companies contribute to the kernel and they participate in that because the kernel is not something that you compete with. It's a common shared resource, just like Kubernetes is. So these companies are contributing to Kubernetes to make things work better for their customers, and they're not trying to make something different from anybody else, per se. They're competing on different areas. Like Linux, Red Hat, and SUSE grew up over the years by competing with service and how they managed kernels for their customers and how they provided service for other people. IBM and Intel contributed to the kernel because they wanted to sell hardware. That was their main model. ARM contributed to it. I mean, other people contribute in different ways because they want to sell hardware or services. But you're not differentiating yourself on the base product. Nobody differentiates himself in the kernel because, again, it's a low-level common good. Same thing with Kubernetes. Everybody sees that there's a lot of work to be done, and they're contributing. I mean, a lot of companies are contributing to Kubernetes. It's great. Companies are getting started based on Kubernetes because that's a resource that companies want, or that other companies want to use. So you can provide Kubernetes hosting for people. You can provide consulting for doing it in-house. Wonderful things like that. But again, it's a common shared resource. They're not competing with it. They're just participating and making it better for everybody. You can't compete on the commons, right? It's a commodity, right?
Okay. So as we begin to draw to a close, I've really enjoyed this conversation. If you woke up from a dream right now and you realized that this whole Linux thing had all been imagined and you're back in 1991, nobody's come out with a widely adopted open source operating system. If you were starting this project from scratch, the Linux kernel, what would you do differently?
Oh, man. We got lucky that we succeeded. I mean, I always say that. Linus picked the right license, was at the right place at the right time. There was a death in the market of innovation in certain areas. We had white box machines come up, and Linux came from below the inside companies and grew out from there. I'd say we'd do it again. We always joked that our goal was total world domination. It really wasn't a joke. We did it. So I think we did a pretty good job. We got lucky. We got a lot of really, really talented people that contributed to the kernel over the years and are still contributing. We were very lucky in that. I'd say do the same thing.
All right, Dan. Greg, sorry.
That's fine.
I was going to say, Greg, thanks for coming on the show. And thanks to Dan Kahn for introducing us. That's why I got confused there. But thank you so much. I really, really enjoyed this conversation.
Great. Thanks. I had a fun time.
You have a full-time engineering job. You work on back-end systems or front-end web development. But the device that you interact with the most is your smartphone, and you want to know how to program it. You could wade through online resources and create your own curriculum from the tutorials and the code snippets that you find online, but there's a more efficient option than teaching yourself. If you want to learn mobile development from great instructors for free, check out CodePath. CodePath is an 8-week iOS and Android development class for professional engineers who are looking to build a new skill. CodePath has free evening classes for dedicated, experienced engineers and designers. I can personally vouch for the effectiveness of the CodePath program because I just hired someone full-time from CodePath to work on my company Ad4Prize. He was a talented engineer before he joined CodePath, but the free classes that CodePath offered him allowed him to develop a new skill, which was mobile development. With that in mind, if you're looking for talented mobile developers for your company, CodePath is also something you should check out. So whether you're an engineer who is looking to retrain as a mobile developer, or if you're looking to hire mobile engineers, go to codepath.com to learn more. You can also listen to my interview with Nathan Esquinazzi of CodePath to learn more. And thanks to the team at CodePath for sponsoring Software Engineering Daily and for providing a platform that is useful to the software community.